turn out the backlights, so that way this video is a little bit better. We're on the electrochemical cell. We're skipping the warm-up. You can turn it out, the backlight for me, because I think it'll appear better. I personally think it looks better, but you can let me know. Okay. Okay, we're on the standard electrochemical cell. So electrochemical cells are portable sources of electricity. And the electricity that's being produced comes from a spontaneous redox reaction that takes place within the cell. We sometimes refer to electrochemical cells as voltaic cells or galvanic cells. Okay, this is the most common application of redox reactions, and there are some different parts to the device that I'm going to mention. The device that I'm referencing is down here in the lower left corner. I'm just going to make this bigger so I can make some notes on it. So when we're looking at an electrochemical cell, we're going to have two half cells, and within each half cell, we're going to have an oxidation and a reduction reaction. So here I have a half cell that is where my oxidation is taking place. And here's the other half cell where my reduction is taking place. Within each cell, we're going to have an electrode. So this rectangular object right here is your magnesium electrode. As an example, they can be different substances. And then on the right, this other rectangular thing is your copper electrode. Okay? Within each half cell, you're going to have a solution. And that solution will likely contain whatever metal this electrode is made of. It will have that metal in ion form in the solution, okay? The two half cells are being connected by this porous U-tube here. And that U-tube is known as a salt bridge. And the salt bridge lets the ions that are in the solution migrate from one side to the other. And it helps maintain sort of like an electrical balance so that the electrons keep flowing, otherwise it would just stop eventually. The electrons are going to be flowing from the oxidation half cell to the reduction half cell. And that's because wherever oxidation is taking place, there's a loss of electrons. So the electrons will be leaving that half cell. They travel through an outer circuit that connects the two. And it travels this way to the reduction half cell because this is where we are gaining electrons, okay? So since I am losing electrons here, what that means is this anode or the electrode is going to be losing mass over time. And then the electrode where the reduction is taking place, this is going to be gaining mass over time. And that's because as the electrons are flowing to the reduction half cell, the ions that are in the solution are going to be combining with those electrons that are traveling here, and you're going to see the metal deposit on this electrode. And that's why it gains in mass. The anode is what we call the electrode where oxidation takes place. And the cathode is what we call the electrode where reduction takes place. Okay? And then you'll have some sort of a device that reads the volts for the electrochemical cell. Okay? Any questions for me? So how do you figure out which direction electrons are flowing in? Well, based upon what electrodes they give you, you would look them up on the SRP table. And you would see which one is on the bottom right. That's the one that would give up its electrons. So if you were to look at magnesium versus copper on the SRP table, which is right here, conveniently, I've got my copper right here. And then I've got my magnesium. I don't think I went down far enough. to this one more time. Your copper's here, and then your magnesium's down here. So this magnesium solid is going to give electrons to Cu+2. You'll form Cu solid. That's what plates on this electrode. Yes?
Why does magnesium lose mass?
Because magnesium is giving electrons, so the solid is going to form the magnesium ions, and those magnesium ions are going to go into this solution here. Does that make sense? So this is your solid magnesium strip here. So as it loses electrons, you form ions, and so they're leaving. Okay? Okay, let's take a look at the next page. Let's talk about the salt bridge in a little more detail. So the salt bridge is connecting the two half cells. It's porous, so that's why it allows ions to migrate and it completes the circuit. And it's countering the electron flow that's occurring. So here you're going to notice that you've got a nitrate anion. And then you've got a magnesium cation, okay? And then here I've got ammonium cations and nitrate anions, okay? So I should have kept the colors consistent, but you get the idea. So the anions are actually going to migrate towards the anode. So here you can see my anode is on the left, and my anions are going into this U-tube, and they're traveling this way to the left, okay? The cations are migrating towards the cathode. So you can see how you've got your magnesium ions in here, you've got ammonium ions as well traveling to the right, which is towards the cathode. They won't always travel in the same direction as the image. You've got to know which side is the anode and which side is the cathode so that you can predict which directions the ions are going to flow, okay? Okay, let's take a look at the next page. Let's go right here. Since a lot of the images for electrochemical cells provide you with, I don't know, they usually have similar detail, but sometimes the detail can be confusing to students. So they often, students often ask, like, is the electrode that's here, or the electrode that's here, is it positive or negative? Well, they have a positive end and a negative end, and it's really similar to if you're looking at like a magnet. Magnets have like a north pole and a south pole, and the magnet might repel or attract things. So here they're showing you that the anode has a negative end and a positive end, and the cathode also has a positive end and a negative end, and the electrons are traveling from the negative to the positive. Think of it as opposites attract, right? So if electrons are negatively charged, they're going to be attracted to the positive end of that cathode, okay, or that electrode. And then down here, since I have my negative cathode down here, this is the negative end of the cathode, and this is the positive end of the anode, well, you could predict that through the salt bridge here, your ions are going to move through that salt bridge a certain way. So the electrons flow externally from the negative to the positive terminal of the cathode. And then you're going to have, since this is a positive end, anions are going to move through this salt bridge towards this positive end of the anode. Okay, so this is the salt bridge, and then the anions are going to travel in this direction. Okay, so internally, the anions go from the negative end of the cathode to the positive end of the anode. Okay, we are skipping this section on non-metal and non-metal ion half cells. So you can cross out this entire section here. We are going to predict standard cell potentials though, okay? So before we get into predicting standard cell potentials, why don't you guys take a look at the quick check here. I want you to do questions 1 through 4 with the person sitting next to you, and let's see what you come up with. Want me to turn the light on? No?
Oh wait, so this
CR above it. CR plus 3. Yeah. Well, no, you don't necessarily.
no, I know. I was just looking at these ones.
Because of AG, so AG is above it.
The CR is
So I'd say the anode is AG. Right.
okay. So which electrode is that?
It's where the oxidation occurs.
It's anode. AG or CR.
So would the CR be green or would the I think it.
They're right here.
That's why I was going to make sure. Because it just seemed to me that the CR plus 3 wouldn't be there. You know, because it has way.
Okay, did you guys get chromium for the anode? How did I do that? Okay. Okay, look at the SRP table.
It doesn't do that.
And you're looking for chromium, and you have CR, CR plus 3, and then you've got AG. So let me just pull this image over.
AG is under the first red. Yeah, so you have it on the screen.
Perfect.
And you have the CR barely on there.
Okay,
That black stuff's kind of covering it.
it should disappear in a second.
There we go.
Okay, so you have your CR with your CR plus 3 here. So you're looking at this half reaction. And then you've got your silver here, right? Okay, so since the CR solid is the furthest one down and to the right, that means that this is where your electrons are going to flow from. Does that make sense? Okay.
Are you looking for one that doesn't have charge or the one that's in the half-life?
You need to look at, you're looking, well, so CR solid is here, right?
Yeah.
And then the CR plus 3 is there. and then the Ag solid is here, and then the Ag plus 1 is here. So you're looking to see which one is on the right side at the bottom, which is
Okay.
this Cr solid. Okay? And then that's going to go up here. So this order will reverse. Agreed? Because this one's going to lose the electrons, and then this one's going to gain the electrons, so that order will remain the same. Does this make sense? Okay. So the electrode that is the anode is the one that's going to be losing the electrons.
That would be the signal.
Okay.
Oh, gains.
Yeah, so this is the one that loses the electrons. So that's why when they ask you about the electron flow, the electrons are going in this direction. Okay. So this is your anode, which means this has to be your cathode. Okay. So the electrons flow from right to left, from the chromium electrode to the silver electrode. In which direction do the cations flow through the salt bridge? Well, doesn't it say on a previous page that cations migrate towards the cathode? So within this salt bridge, your cations are going to migrate in this direction, from right to left. And then which electrode gains mass? Well, whichever direction the electrons are going to, okay, that's the one where these silver ions are going to combine with these, and we're going to get silver plating like on this electrode right at the bottom of it. Okay, so the electrode that gains mass is silver. You okay? Could you do this on paper? You need to be able to do this on paper. Hint, hint. Okay, like this will be a quiz. Hint, hint. Okay.
Is there any more practice with
Okay.
that, or is that it?
Yeah, there is a practice.
Okay.
Yeah, it's not for points, but there is a full practice problem at the end that I put on Canvas with the
That's good.
answers. And you can also use your phone to scan it.
That's great.
Okay?
Good practice.
Okay. So let's, number 2. Let's go on to predicting standard cell potential. So I believe this was back here, the very bottom. Okay, so since we have kind of a simple design to deal with on these electrochemical cells, we can use the SRP table and their standard cell potentials in volts to figure out the voltage produced depending upon what our reducing agent and our oxidizing agents are. So what I'm going to do is, let's go ahead and turn to the next page and go underneath the quick check here. So on your SRP table, the hydrogen electrode is your reference electrode. You will notice that the hydrogen electrode has a 0 voltage for its reduction potential. So do you see here how this is shaded and it says 0 volts? This is your hydrogen electrode. That's what everything is compared to. So if you would do me a favor, I would just highlight that all the way across in a unique color so that you know that that's the reference electrode. Okay? So above this reference electrode, do you see how all of my reduction potentials are positive? And then below it, all the reduction potentials are negative? Okay, so what this means is that if you're underneath it, you're losing to hydrogen by that many volts. And if you're above it, then you're winning against hydrogen by that many volts. Okay. Let's go to the next page. Let's go right here. If we're using the SRP table and you have to reverse the order of something, like reverse the half reaction for something, then make sure you also change the sign on the reduction potential. So as an example, if I said to you, we're going to have copper metal giving electrons to silver, okay? Then you would have to reverse the order of this half reaction because the copper metal is further down and to the right. Agreed? So when you're looking at its reduction potential here, which is a positive 0.52, you would flip the sign and you would make it negative 0.52 volts. Okay. If you multiply this half reaction by a whole number to get the electrons to match another half reaction, you do not multiply the reduction potential by that whole number as well. Okay. Okay. Let's just go ahead and jump into some practice. Let me have you underline one quick thing here. A positive reduction potential means the reaction is spontaneous. And a negative reduction potential means the reverse reaction is spontaneous. Go ahead and turn to practice problems on the next page, which are right here. Okay? I'm going to do number 1 and then I'll let you do number 2. For number 1, they're giving you a nickel half cell and a bromine half cell. You have to look at the SRP table to see where these substances are located. So if I bring up the SRP table here, you've got your nickel half cell down here. Here's your nickel solid. And then you've got your bromine half cell here. So your electrons will flow in this direction from your nickel solid, which is this, right? So this is at the bottom left. I'm sorry, the bottom right. And it's going to flow to Br2, which is at the top left. Does that make sense? Can you see it? Okay. So you're going to have your nickel half reaction reversed. Your voltage for that is going to be a positive 0.26. Bromine is going to stay in the order that it's in. And this is a positive 1.09 volts. Electrons will cancel. And then you're going to add these two voltages together, and you're going to get 1.35 volts. Does that make sense? I think I should write in black. I think it's easier to see. Okay. So what I'm going to have you do is I'm going to have you do number 2. And then in number 2, they gave you this half cell and this half cell, and it's pretty common for them to put these parallel lines in between the two half cells. Okay? So with the person sitting next to you, why don't you come up with the overall reaction and the standard cell potential.
So the electrons aren't balanced. We have to balance them out. Okay.
Unfortunately, yes.
That's fine. So I'm just going to preempt that then.
use the copper. You use the one that says the Cu plus 2. So do you see how that says Cu plus 2 here? Is that, I can't, yeah, that's right. This is your Cu
You're
plus
right.
2.
Yep.
So you're going this direction. Does that make sense? Okay. So this is in the lower right. And then this is in the upper left. So this is the direction of electron flow. So no, you don't have to write lower right. And I just do that for you so that you can see which direction the electrons should be flowing.
I'll be surprised when I do this one.
Why did you reverse the pale reaction?
This one has to be reversed because whichever one is down here in the bottom right, you always reverse the order of this half reaction and you change the sign on the E.
Can I get a positive?
I got 2 volts.
You have everything, right?
Okay.
Except for the volts.
All right. Make sure you cross out non-standard conditions underneath this question
So why is it 2 volts?
because you add those two together.
I thought the copper was 0.15, or is it because you multiplied the volts by 2?
No, are you looking at the copper is 0.34. It's I think there's 2 coppers, so you might be looking at the wrong
Yeah,
copper.
one of them had a solid next to it. I didn't see that. Hi, Mrs. Golden.
I know. How you doing?
Good, how are you? That's what it was. I didn't realize it until just now.
Okay, I'm just gonna keep going. Is that okay?
Yeah, that's fine.
I have to finish a section today, so it's not gonna take me that long. We're crossing out a bunch of things. Okay. So cross out non-standard conditions. And then cross out cell equilibrium. You do not have the Nernst equation. You do not have the Danieli cell. You're on common cells and batteries. Okay. All right, so cells that are used in electronic devices are called dry cells because the electrolytes are in gels or pastes. They're not in a solution. If they were, they would probably leak. A battery is a group or battery of cells. The common 1.5 volt battery that's used to power portable electronics is actually an alkaline dry cell. And the reason we call it an alkaline dry cell is because the contents for an alkaline dry cell consists of zinc powder packed around a brass pin. Here is your brass pin here. The powder is here. It's in the middle of the cell. And then the cathode is a paste of manganese dioxide and powdered carbon, and that is surrounding it here. The 2 electrodes are separated by a fabric that has pores in it, and we named this an alkaline cell because the electrolyte is a base potassium hydroxide. Okay, these last pretty long, and they have a steady voltage. If you take a look underneath the figure here, you'll notice that other related cells would be button batteries that are in calculators and watches, or nickel cadmium batteries, or lithium ion batteries. Okay, they're used in cell phones and electric vehicles. Take a look at lead acid storage batteries. So a lead acid storage battery, let's not talk about its contents. Go ahead and turn to the next page. This is what a lead acid storage battery looks like. the lead alloy grids are packed in a spongy material, and they are in sulfuric acid. And they don't have a separate anode or cathode because the oxidizing and reducing agents are both solids. Let's take a look at fuel cells. Fuel cells have their reactants resupplied to them by some sort of external force. This is used in electric cars and buses, and it also provides electricity for vehicles and space travel. They're rather efficient. Let's turn to corrosion. Corrosion is an example of an unwanted oxidation reaction. Rusting is the corrosion of iron. We can actually prevent the corrosion of iron by covering it with something else. So if you turn to the next page, if you protect iron by painting it or putting grease on it, we call that cathodic protection. Galvanizing it will also protect it from rusting. Okay, so this happens to things like deep sea oil rigs and ship hulls or underground pipelines. Sometimes we may specifically coat iron with zinc, which is what galvanizing is. And what happens is the zinc on the outside is going to react, and so we call it the sacrificial metal. So we sacrifice that metal rather than what metal is underneath it. Does that make sense? So that's it. We're done with the section.